Hi class, welcome back to Electromagnetics. I'm going to continue our discussions on antennas, and today we want to take a look at the half-wave dipole. Thought for the day, thought I'd change things up here just a little bit. Again, with another saying that I personally use a lot and encourage others with, and that's saying Mark Twain used to say was, if you tell the truth, you don't have to remember anything. And I guess this one was brought back to my mind by seeing the recent presidential elections. No matter which side you're interested in, they seem to exhibit this. I know I would hate to be a politician and have years and years of video of me saying things and worrying that I would ever contradict myself. And I think that's kind of the point of this is, hey, if you just keep telling the truth, you don't have to remember what you said before, just keep telling the truth. So I think there's a lot of wisdom in this saying, so just something to think about. So we're continuing on with part 9, antenna basics. This is the third lecture, again, half-wave dipole. So we started this section by considering first an infinitesimal Hertzian dipole. And this was useful in setting up the math and coming up with theoretical analysis. But of course, this isn't practical for real life. So we want to take a look at a specific application of the Hertzian, which is very practical and is used quite a bit in the real world, but it is also one of the simplest antennas, and that is the half-wave dipole antenna. So again, this is a specific application of the Hertzian, so because of that, we can utilize as much of the analysis that we've already done and reapply it here, as we'll see. So the way we set this up is we want to first have a current source that's defined here in terms of Z. So we're lining up on the Z axis. And so you'll see it varies both with position and with time. And the graph of this here, this is Z equals 0, Z equals L over 2, and Z equals minus L over 2. And the thought of this is that from this tip to this tip, that whatever we're feeding this with, whatever source, that's going to be the exact length of a half wave. And we'll see the importance of that here in just a second. So we notice that with this configuration and this source current definition, if we were to take those bent pieces and straighten them out, this would look like just a transmission line, right? And it's an open circuit transmission line. We know from previous analysis that that's going to create a standing wave on our transmission line on our antenna. And so that's that's important here, and that's the purpose of making it the length of a half wave. So with this now, we can model this as a series of infinitesimal units of the Hertzian dipole. So from minus L over 2 to L over 2, you see we have these infinite number of Hertzian dipoles lined up in a row or in series. And so all the math is set up exactly the same as we did with the Hertzian, so all this should look very familiar, and we'll use the same approach. So we already know what the equation is for 1 Hertzian, right? So that would be this equation here. Well, we have to consider that this is a differential E field and a differential H field, or electric and magnetic field. So we have to sum up each of these infinitesimally small Hertzian dipoles. Each has a contribution to our point out in space. So naturally, what we need to do then is we need to integrate this from minus L over 2 to L over 2 to get the expression for the entire electric and magnetic fields. So let's look how we do that. So of course we just applied calculus principles, so it's just a simple calculus, well maybe not simple, but it's a calculus evaluation. I didn't want to go through all that again, saving time. If you in the future take a antennas course, you'll probably go through these calculations, but for the purpose of just the introduction, this is the equation for the half wave. And again, you can see that this is the equation for the electric field, and this is the equation for the magnetic field, and they are dependent on the angle and time and the radius away from it, from the source. So just like before, we want to take these expressions that we have for the electric and magnetic fields, and we want to calculate the Poynting vector for the half-wave dipole. Of course, we do that by taking the cross product between the two, which would result in just E theta H phi in the direction of the AR. And so when we plug these values in, we come up with this general expression here. And so the Poynting vector then can now be used to compute an expression for the radiated power, just as we did with the Hertzian. And when we plug those numbers in, again, just to save time, our expression for the radiated power for a half-wave dipole is this equation here. So by observation, just like we did before, we can take the time average of this, and of course the time average, the only part that's dependent on time is the sine function here. It has the t in it, and of course we remember from before the time average of any sine squared is just going to be 1/2, and so this time average reduces to this equation here, and we know from before this 1/2 I squared, this part would be the R of our power equation, and so that's what we defined before as our radiation resistance. So for the half-wave dipole, the general equation for the radiation resistance is 0.609 epsilon over pi. But again, we're going to consider that we're almost always using this in free space. So the eta is 120 pi, so the pi's cancel, and so it's 0.609 times 120. And so that's where we come up with the radiation resistance for a half-wave dipole antenna when propagating into free space is 73 ohms. It's a very common factor there if you deal with these types of antennas. So finally, we can now derive an expression for the average and maximum power for the half-wave dipole, which, just as before, we will use to compute the directivity. So when we look at the radiated power, to maximize this part of the equation here, we need to know what the maximum of that is. And of course, since they're trig functions, that would naturally just be 1. And so this reduces to this equation where this part is just replaced with the number 1. And then we have the average for this. And again, if we average that out, we come up with this expression here. Again, I'm skipping a lot of the math steps again because I don't want to spend a lot of time on that. I just want to introduce you to some of these equations and how they're used. So now that we have the maximum and the average, that's what we need to calculate the directivity. And so we'll do that on the next slide. So here, remember that the directivity for an antenna is defined by the maximum power radiated in any direction divided by the average power radiated around the sphere, the complete encapsulation of the antenna. And so we just calculated these on the previous for the half wave. So we plug these values in. We end up getting 1 over 0.609, which calculates out to about 1.642. And so we recall from previous lectures that for just the Hertzian, of course that's the theoretical infinitesimal antenna, the directivity was 1.5. So therefore, the half-wave dipole antenna is slightly more directional, which, if you are wanting to transmit between two separate sources where you have a transmitter and a receiver in a specific location, then the half-wave dipole would be slightly better for that application. And again, as before with the Hertzian, the radiation pattern and the radiated power patterns look very similar. Again, there are these double lobes on each side of the antenna moving out in this direction. So again, if you had a source, if you placed it over here, you wouldn't get any signal from here, but as you start to move the source or the receiver around here, as soon as you got into this field or this range, then you start to pick up a signal and be able to receive whatever is being transmitted on the antenna.